Okay, hey everybody. Thank you so much for tuning in. This is the Algebraic Geometry seminar. We're going through Vakil. Right now we're in chapter 1, section 5, going on homology and cohomology. And I think really the bigger part of this is we go through existence and uniqueness and then short and long exact sequences in homology, cohomology. So I want to start not actually with Vakil. I want to go through a paper that I wrote recently for my topology class because I had to explain all of this stuff. Um, or rather, I wanted to explain all of this stuff, and I thought it was interesting. And then we'll go back once we have some intuition. We'll do some exercises. Um, so let me go ahead and share my screen. Um, so we'll have to do a little bit on sheaves, but that's not a terrible thing, as you'll see pretty quickly. Um, yeah. Okay, so um, the kind of idea of this paper was that I wanted to motivate um, basically Zariski topology, topological continuity into like the idea of sheaf gluability and like basically say how do these things interact from a topologist's point of view. And then I kind of abandoned the topologist's point of view for a while, and then I kind of tie it all together with like a topological intuition. But either way, I feel like it turned out pretty well. And so we've talked about a lot of things in the first kind of half of this lecture series, going from Hartshorne, and that was my reference text for this, except for part 6. Um, and so basically, what I want to do is I want to give the same motivation. I want to talk about sheaves as this kind of notion of gluing things together, and like there's something that we've already seen and worked with in terms of sheaves on varieties. And then I want us to talk about the cohomology of sheaves and then go kind of where Vakil goes. So we can go ahead and just skip 3. So this is just kind of chapter 1. We talked a while ago about the fact that dimensions of varieties like kind of induce things about dimensions of their invariants, like the ring of regular functions and local rings, stuff like that. And actually, for this paper, it's not super professional. As you can tell, I ended up taking something from one of our lectures and like tossing it in there to talk about morphisms of varieties. Um, and so the ring of regular functions on Y is like our first invariant, and it's actually kind of sort of our first example of a sheaf. If we well, really, it's our example of a pre-sheaf, but it'll make sense in a second. And so um, then we have local rings, all these things, and like the field of functions, right? All of these things are good examples of like pre-sheaves. So when we say pre-sheaf, you should kind of start thinking about these invariants. And it's just all of these things that store data in terms of inclusions. And that's like a really useful thing. We talked somewhere in here in Hartshorne about a natural injection from the ring of regular functions to a local ring to the field of functions. Um, but this natural injection is like a natural injection of pre-sheaves. So you can define this other sheaf on that. Um, and so yeah, it just kind of like comes together to say, okay, this is something you know. And this is something that you know because of basically dominant rational maps, right? So a rational map is the equivalence class of pairs of open subsets and then morphisms under this equivalence class of basically gluing morphisms together on intersections of open subsets, right? And this is exactly a sheaf, right? So dominant rational maps um, on like the spectrum of a ring or on something like that, right? That is a sheaf. Or on a variety, or on the regular functions on a variety with this dominant rational map idea, that is a sheaf. Um, and so it is the idea of like you have this data that is stored in terms of inclusions and open subsets from some induced topology, and then you put that's a pre-sheaf, and then to sheafify the pre-sheaf, you basically add some kind of notion of gluing morphisms together on intersections of open subsets, right? And so in here I talk about birationality and all of this stuff. If you want to read the paper, it's on my GitHub. It's kind of a fun paper. And so yeah, this is a great quote. You'll ask an algebraic geometer what a topological space is, and they'll go on a tangent about how really a topological space is just something you can put a sheaf on, and that a sheaf is really just something that gives you a good cohomology. So really the question you should be asking is what cohomology is, right? That's kind of the point of today's lecture. And really this whole paper just kind of felt like a man, this would give a good cohomology kind of like meme.
Glad you were able to add the jokes in like Vakil.
Yeah. It's really funny. I got this from an Instagram screenshot. That's why it's anonymous. I don't think it should be cited. So, and actually, it's even worse than that. It's not just an Instagram screenshot. It's an Instagram screenshot of a Tumblr post, and I don't think I should be citing that in an academic setting.
That's great.
Yeah, it was something. A lot of this was written pretty late at night. Finals was getting to me. But yeah, so a pre-sheaf technically a pre-sheaf is this kind of inclusion mapping of sections or stalks of abelian groups, and this is induced by this mapping F. So for every open set, we induce an abelian group on it, and then we have this kind of direct product of abelian groups, and that forms the pre-sheaf. But it's worth noting that since we're working in an abelian category, pretty much strictly, like this is just kind of saying we group together things that like we can treat as stalks of the sheaf. And then for every inclusion of open sets, or like some open set is contained in another open set, then we can basically have a restriction map of like the morphism on that section. And so this is just kind of the idea is that we can restrict things down. And that restriction map is an identity, or has an identity map, and then also has a transitive map. Later on, so we're going to see this as a few things. So gamma here is what's called the functor of global sections. And so this is just like a way that we're going to characterize pre-sheaves later. And then when we talk about cohomology, basically the zeroth cohomology group is a pre-sheaf. Don't worry about that too much yet, but it'll make sense in a little bit.
All right.
And so you're already familiar with pre-sheaves. Like I said, all of these things are interesting pre-sheaves. And so you have like functions on open subsets, and then regular functions and vector fields, differential forms. Maybe we're not familiar with because we haven't talked about them, but like we watch it on YouTube might be. And then solutions to PD. This is my kind of favorite example of a pre-sheaf because this is really interesting. So solutions to PDEs on open sets in R like really induce like an interesting sheaf to study. Like even though we are largely concerned with algebraic geometry on varieties, you can use a lot of the firepower of algebraic geometry that comes from sheaf theory on solutions to PDEs or ordinary differential equations. And it gives this really cool cohomology. But yeah, basically each of these examples encodes local data, doesn't tell you how to glue them together. Sheaves do. And so a sheaf satisfies the following two axioms. And basically, it's a pre-sheaf that satisfies these two axioms. And it's worth noting we're defining a sheaf and a pre-sheaf on a topological space, but really you put a sheaf on an example of like a topological space. So it's a topological object, but it's really not. So locality, if we have two sections of the pre-sheaf that agree on a restriction map, then they're equal, and this is our theorem, right? So in this paper, I referred to this as the something or other gluing theorem, the morphism gluing theorem. No, it was way down. Yeah, morphism gluing lemma. It's exactly this. And so when I said earlier, like we have seen examples of sheaves, we have seen examples of sheaves. And then the second portion is existence. And so this is where I think this is like the thing that should make sense. This is where I think of this as gluing.
Yeah.
And it's basically if we are given a section that agrees on like the overlaps, then basically like you can find a section on some open subset where you just have like its own dedicated section. And this is where the picture is that, okay, if you have two open subsets that interface on this intersection and they agree on this intersection, then by the notion of a topology, right, finite intersections of open sets are open. And so we should have another open set there that is also a section of the sheaf. And so this leads to a very natural construction called the structure sheaf, which is the collection of regular functions on U. And it's the collection of local rings. Is this different than the ring of regular functions? I am pretty sure no. Yeah, I'm pretty sure it is. No, it is different. It is definitely different. Yeah, the structure sheaf is defined specifically on an open subset. But if it's just OX, then I think it is the ring of all regular functions because it's that. No, it's definitely not. This is definitely a larger set than O of Y. So I'm just gonna call this in terms of like convention. I'm gonna call this OX. So OX is the structure sheaf. So when we're considering OX, it is all of the rings of regular functions for every single open subset in here. And so this acts a lot like basically taking the union of all of our local rings and all of the localizations of unions of local rings. More examples that we don't care about because we're not doing sheaves today. There's this thing called the skyscraper sheaf, which is like fairly intuitive. I linked a really great YouTube video. This guy is awesome. We're going through a kind of a slow pace because I don't know this material very well. But this guy does algebraic geometry and is like a PhD, and so he knows it really well, and so he has some really great YouTube videos. But yeah, so because this is for a topology class, I started saying, okay, well, we want to think about homology. We can start thinking about homotopy as a motivator. And so I'm going to skip over this paragraph here because we haven't really covered anything about the fundamental group, but you know, those interested might be interested. And so then, yeah, short exact sequences, this is where we kind of get to the stock standard definition. So a complex at B is a sequence where basically the mapping of, basically F composed with G should be 0. And is exact at B if the kernel of G is equal to the image of F. And so moreover, a short exact sequence is a complex which is exact at A, B, and C, and is of the form 0 goes to A, goes to B, goes to C, goes to 0, right? And so when we're thinking, and this is a very categorical way to describe um, like complexes, there's like a visual, very, very visual like understanding of complexes that I honestly haven't been able to reconcile with the category theory version. And I like the category theory version a lot better because it applies in general. So what we're going to show in this paper is that like, okay, cohomology of sheaves exists, and then we're not going to worry about computing it. And so, yeah, basically, when we talk about short exact sequences, they're things that look like this, and then the kernel of G is equal to the image of F. Um, and then it also should be that, you know, the thing that goes into A has that the kernel of F is equal to the image of this map from the zero object into A, right? So it kind of like it's exact at A, B, and C. And so then if we have a complex at B, we define the homology group H of B to be the kernel of G quotient the image of F. And so it's worth noting that we're defining homology groups on a complex, not on short exact sequences, right? So if we have an exact sequence at B, right? Like if we have a sequence that's exact at B, then the kernel of G is equal to the image of F and the homology group is trivial, right? But if we don't, then like, okay, we have something new going on here. An important note from an algebraic perspective. So groups, rings, and modules all have the property that like the kernel is a normal subgroup of its object, and then the image is a normal subgroup of its object. And so basically this gives us the ability to quotient. And actually, I'm not sure that the image needs to be a normal subgroup. So maybe it's just the kernel. But that's the important part because that's what never mind. It is the image. Maybe that does have to be a normal subgroup. Yeah. And the topological intuition here is that we call the elements of the kernel cycles and the elements of the image boundaries. So we think of homology at B as cycles mod boundaries.
Okay.
And so the image here is like cycles, like if you think of like a torus, so like a donut, cycles are kind of like the loops that you can construct on there. You could theoretically construct one that continuously deforms through the center hole, except for the fact that we mod out the boundaries, which like enforces the restriction on the fact that it has to either loop around the entire donut hole or it has to be a trivial loop that can like contract back to a single point.
Okay.
So those mod boundaries is like this way to intuitively collapse everything to its boundaries and to tell us like how many holes are in a chain complex. And so if we can endow like a topology on B, right, then the homology group at B basically tells us how many holes we have in the object. Now that's kind of a loose way of saying it, but it's a good way to think about it. Is the rank of your group tells you how many holes you have in your object. Whereas like the group itself tells you other things. And so homology shows us what gets left behind when we move on in the sequence from B. And so cohomology is this kind of reversal of things. And I'm realizing that I start talking about what cohomology does before I define it, right? So homology shows us what gets left behind as we move through G to C. Cohomology detects basically failures of right exactness after we apply a contravariant functor to the sequence. The intuition for the cohomology of sheaves is basically saying where does the gluability of pre-sheaves fail, right? So that's what cohomology tells us in terms of cohomology of sheaves is where do gluing things fail? Where does that go wrong? Um, so if we want to relate short exact sequences to each other, we do so functorially. So a functor is a left exact functor if it preserves the exactness of the first two elements of every short exact sequence, right? So this is like cover up C and 0. It can go off to wherever, right? But this would be a left exact functor, right? And then similarly, a right exact functor, cover up 0 and A, that can go off to wherever, but then it goes B, C, 0 at the end of it. And so basically, this is the notion of like preserving right exactness. And then kind of the idea of this is that um, basically, how do we measure the failure of right exactness or left exactness? And then depending on the type of object and sequence that we're studying, what does that tell us in terms of stuff that we care about, like failure of gluability for sheaves?
Mm-hmm.
Um, so the language that's typically used to talk about cohomology in terms of functors is this thing called a derived functor. Um, And to set up derived functors, we need these things called injective and projective resolutions. Um, and like I said in the paper, I don't really have a great intuition for like how these tie in, besides that they force things to behave nicely. So it sets up these things called spectral sequences, which are going to kind of deliberately avoid. For people watching on YouTube, I need spectral sequences for another thing that I'm trying to read through, and I'm likely going to do an entire lecture on this in the playlist for Galois cohomology and class field theory. So if you made it this far and you're following along for some reason, and you maybe think that I have a good explanation of things, look out for that in a few days from now. And I don't know if that will be a great explanation because I'm really getting very far out of my comfort zone in terms of what I feel comfortable lecturing on. But I want to keep putting these out there because it shows that like we're working through these things and like we're really wrestling with things, and I think that that's nice. And maybe it'll help people who are also wrestling through these things, and maybe there'll be something small that I say that like makes it click.
Yeah.
But yeah, so if we have an abelian category, we have this thing called a resolution, which is an exact complex together with a morphism from R0 into A, such that the sequence is exact at every Ri and at A. And so if each Ri belongs to the class of injective objects or projective objects, then it's called an injective resolution or a projective resolution.
Mhm.
Um, and so a left derived functor is basically this thing that acts on right exact functors. And it tells us the failure of the left hand um, exactness. And so to define left exact functors, so we have this left exact functor, assume that every object of our abelian category admits an injective resolution. Then we choose an injective resolution that goes, I didn't put this up here, but like the chain for this goes this way because it's a left exact resolution for
Yeah.
injectivity. And then instead of Ri, we have like I to the I.
Mhm.
And so applying F to this resolution gives a complex where we just have this functorial sequence. And I think it is by intention that I omit a F of A in this chain complex.
Mhm.
I think that that is intentional.
Wait, is f of a 0 because it's
No, I think F of A is the limit of this spectral sequence, but
okay.
that might not be the case. Um, yeah. Oh, okay, yeah, that is exactly what it is. So basically, you can picture F of A as an initial object,
Mhm.
where it's mapping, no, it's a final object because it maps out and all of the fi sequence projects down into f of a. And so it is, you can kind of think of it as the conventional limit of this sequence. But yeah, so then the ith right-derived functor, okay. Wait, did I do that right? I trust myself, that's fine. Yeah, the ith right-derived functor of f is defined to be the ith cohomology group of this complex. And then this I dot is the injective resolution. And so basically what this says is that the ith cohomology group denoted by h to the I of the left exact functor of I of the I chain is equal to the ith right derived functor of f of a. And so this is where it would be nice to draw a picture probably. But the relationship between the ith right derived functor of f and then like this I chain is that we're measuring the failure of right exactness in this injective resolution. Right, so like if this sequence stabilizes eventually, then we go to a zero object, and then the failure of right exactness is some number of things out here to the right.
Okay.
And so the right derived functor measures the failure of right exactness of this left exact functor.
Yeah.
And that is exactly what cohomology of sheaves is. And so the failure of right exactness, because it's an injective resolution, well, we're basically saying that A injects itself into this thing, which may or may not stabilize eventually. And so, like, the stabilization or lack of stabilization, like we could think of this with like finite abelian groups as stabilizing into subgroups down into the trivial group. Then you're like picking paths through all of the subgroups of your finite group. So if you have like the symmetric group of like 5 elements, then you know that you have the alternating group of 5 elements as a normal simple group. But then you also have like the alternating group of I think 3 elements in there. You have Z5 as a subgroup, and so you can pick these paths as injective resolutions that kind of go backwards. And so you can inject down to the trivial group because that will stabilize because it's a finite group. And then that is your injective resolution. And so then the ith homology group, or sorry, cohomology group of this cochain complex, like basically is the right derived functor of that. And then the definition of left derived functor is the exact same, but we switch the sequence that, or we switch the resolution direction, and it's projective resolution now. And then we apply a right exact functor, and we use the left derived functor to measure failure of left exactness.
Okay.
Left-derived functors tell us about homology groups. Right-derived functors tell us about cohomology groups.
All right.
So, like I say in the paper here, okay, yeah, I think it is a mistake. This is supposed to have f of a here.
Okay.
Um, Yeah, so with cohomology, it's very much the way we've constructed it, kind of overkill.
Mhm.
Um, and so here we want to measure the failure of gluability of sheaves. And so if we're thinking of cohomology as failure of right exactness, then this for the cohomology of sheaves is just failure of gluability.
Okay.
Um, and so we need to define this thing called the global sections functor, which is a right exact functor, but generally is not a left exact functor. And so if we have a topological space, let SH denote the category of sheaves of abelian groups on this topological space. And because we're working in an abelian category, this suffices to be like Z modules or anything else. Then the global sections functor gamma from sheaves to category of abelian groups is defined by topological space with some pre-sheaf on it is equal to the pre-sheaf of the topological space. And so the abelian group of global sections over the whole space is this f of x here. And so a morphism of sheaves phi from F to G is the induced map on the same topology of two different sheaves through this global functor, right? So
Mhm.
remember, functors take things from their objects to their objects and from their morphism sets or classes to their morphism sets in the
Okay.
two categories. And so
Yeah.
basically, the topology induces the mapping, um, but then the functor induces the agreement between morphisms.
Mhm.
Um, and so, yeah, this kind of gives us an intuitive way to think about these things. We extract the global data of a sheaf and assign to each sheaf its group of global sections. Um, and I'm sorry, I was mistaken. I said it was right exact, but not left exact. It is left exact so that we can use a right-derived functor to get cohomology. It is usually not right exact. In this paper, I only talk about affine geometry, so that's why there's like
Okay.
all this composition about it. But yeah, basically, if it's not a quasi-coherent affine scheme, it doesn't have like homology defined this way. Don't worry about that. That's fine.
Okay.
But basically, we obtain the cohomology of a sheaf by taking the right-derived functors of the global section functor. And so basically, it is, the ith right-derived functor, Ri, looks like the ith cohomology group of the global sections of some injective resolution into the sheaths that we care about.
Mhm.
So basically, we're looking at some injective resolution of global sheaf sections into the sheaths that we care about, and then we're looking at the failure of right exactness of that injective resolution. And then within this framework, the zeroth cohomology group recovers the global sections themselves. And that just kind of goes up here. When we first defined, it wasn't gamma. Yeah, when we first defined a pre-sheaf, this is exactly what we mean.
Yeah.
The zeroth cohomology group for covering the global sections. Um,
Right.
So, as a final remark on sheaf cohomology, we don't compute cohomology this way, right? What we have shown is that we can constructively build out this thing that we're going to call the cohomology of a sheaf, but that we're going to need to compute it some other way. Um, so it always exists. It is the universal way to extend global sections functor gamma to a cohomological functor h. Um, and this kind of, you can think of HI, right, as an element of its own long exact sequence. And so a long exact sequence is a collection of short exact sequences, where we can really visualize this business of the right-derived functor of gamma as being short exact sequences. And for each I in our cohomology chain, it gives us this expansion of short exact sequences into capital I, let's say, many short exact sequences that inject into each other. And so we'll talk about this in the context of Vakil because he does a great job setting that up. But basically, we're extending the global sections functor, which is just well defined on a sheaf, to a cohomological functor, which gives us something in long exact sequences. To compute anything about cohomology, you need this thing called the check cohomology for cohomology of sheaves. And the downside is that sometimes it doesn't work, but that's for its own reasons, and we're going to talk about that in due time.
Okay.
So yeah, that is like the thrust of this paper. If you want to read it again, it's on my GitHub and my LinkedIn. So either one of those
Okay.
places is a perfectly reasonable spot to find it. But now we can go ahead and start talking about Vakil. Let me just go ahead and set up my notability file. So are there any questions?
Not that I can think of. I'm
Okay.
sure they're gonna come in due time, but
Yeah. A, G. Okay, now let me screen share. Okay, so without further ado, I'm gonna skip some of the things that we've already covered in Vakil, but then I'm going to throw in the exercises about them. And this will kind of go by our usual thing. So theorem 0 into A into B by F is exact if and only if F is a monomorphism. And then A into B into 0 by, nope, by F is exact if and only if F is an epimorphism. And so again, monomorphism and epimorphism are kind of this way of characterizing left cancellation and right cancellation. And I have a note written down here that references another note that I'm trying to decide if we need. Where? Sorry. Yeah. So monomorphisms are right cancellation. So if we have pi u1 is equal to pi u2, then that implies u1 is equal to u2. And then an epimorphism is the other side. u1 pi equal to u2 pi implies that U1 equals U2. And so the reason why we get exactness out of this is that basically the kernel of F equaling the image of whatever this morphism is has to kind of force this composition on the left about U1 to be unique. Right, so we can say if we have, like, if this is pi, and then this is U1, if we had another way to get here that ends up being the same in B, then, like, it has to cancel out. Otherwise, the kernel of pi won't equal the image of these two things. It's worth noting that, categorically speaking, the kernel is not a set, it's a morphism, but like we usually induce the kernel object, and that's usually what we mean. Similarly, for an epimorphism, the business of right cancellation is that this would be pi, and then this would be U1, and this would be U2. And that otherwise, if the kernel of U2 wasn't equal to the image of pi, then we wouldn't go to 0. I think that's right. And so before we try and prove anything about homology, I do want to try and prove this thing called the snake lemma. And there's a specific proof that I want to pull up because it does a great job. So the snake lemma is a very famous lemma, and I'm pretty sure there's a movie that it shows up in. Let me Google that. What movie does the snake lemma show up in?
It's my turn.
How did you know that?
Looked it up.
Oh, okay.
I just typed a bit quicker.
That's funny. Okay.
I was
Yeah.
like typing it in before you said you were going to.
Yeah. So then let me go here and let me find it. Snake lemma. There we go. Okay. Yeah. Okay, so consider snake lemma. We're going to be thinking generally about just ring modules and ring module homomorphisms because we have Freyr's theorem that lets us map everything back into modules. This diagram that I'm going to present is universal. So if we have this, and then we have A prime, B prime, C prime, 0. And then we have morphisms that inject like so. Then basically we can create a long exact sequence that gives us a nice property about the commutivity of kernels and co-kernels. And I guess I should take the time to label alpha, beta, and gamma.
Yep.
And this is F and G and F prime and G prime. So we have kernel of alpha goes into A, then kernel of beta and kernel of gamma. Like so. And then we're going to show something that's going to be kind of neat, because we're going to define yet another row where it's going to be the co-kernel of alpha into the co-kernel beta into the co-kernel of gamma into 0. And this all flows down, but we're going to get, oh, and I guess this should also go, nope, that doesn't, for certain reason, and we also don't have this 0 object, because the whole point of the snake lemma, and I'm going to do this in yellow, is that we get this other morphism that wraps around. And so we get this long exact sequence, 0 into kernel of A, into kernel of B, into kernel of gamma, into co-kernel of alpha, into co-kernel of beta, into co-kernel of gamma. And we're going to call this D, or differential. And so the snake lemma says that basically let's see. That this delta exists, is well defined, and then is exact. So basically, we want to say that I think this is a long exact sequence. Hold on. Lemma. Yeah, the basically the long exact sequence here. Yeah, that is long exact. And the delta exists. Okay, so proving it. Let's go through this. Proving. So we need preliminary definitions and lemmas, as usual. So just to recall the co-kernel, so alpha from A to A prime has co-kernel of alpha is equal to A prime quotient the image of alpha. And then as a preliminary lemma, let A and A prime be modules over a ring R, and alpha is an R module homomorphism. Then 0 into the kernel of alpha into A into A prime by alpha into the co-kernel of A, or co-kernel of alpha. I keep saying little a. I mean alpha, usually. This sequence is exact. I.e. for each of the morphisms in here, the kernels and the images match up. So starting first with the kernel of alpha, it's exact at cur alpha because the map into A is an injection, and so we get kind of the natural thing that we want there about the kernel and the image lining up. It is literally the image of the previous injection at A, right? So like if we're saying the kernel of alpha is equal to the image of whatever this map is, that is just literally like this thing. So that one lines up very nicely. And then the map from A prime into the co-kernel of A is the natural projection map mod the image of alpha.
Okay.
And so again, this is just literally by definition that like it is exact at A prime.
Yeah.
And then this projection map is surjective, basically by construction. And then the image is equal to the kernel of the map to 0, also by construction. So, any questions about this lemma?
No.
Okay. Then as a second lemma, we're going to prove that 0 to cur alpha to cur beta to cur gamma is exact. And then we're going to show that the co-kernel of alpha into the co-kernel of beta into the co-kernel gamma into 0 as two separate sequences are both exact. And so to do this, we're going to need to define some names of these morphisms. So we're going to call this F naught, F1, no, F naught and G naught, sorry. And then we're going to call this F2. That doesn't make sense. Oh, it does make sense. And G2. And then kind of reconciling this is F naught, G naught, F2, and G2. So does that make sense?
Yeah.
Okay. So starting with the sequence of the kernels, let me just like write that down. Start with 1. We can see that the map of, or rather the image of the map of 0 is 0. And so if F naught is injective, then the sequence is exact at cur alpha, right? So basically the kernel of this would be 0 if it's injective, and then this map has an image of 0. And so then that works out nicely. And then I'm following someone else's proof for this. I'm following my Algebra 2 professor's proof for this. And so I'm trying to decide if we need all of that. Yeah, so I guess this is actually a really great boilerplate. Unsurprisingly, my professor's awesome. But yeah, let's go through it. So so let X in the kernel of F naught. Then since this diagram commutes, F naught of X is equal to F of X in the big diagram is equal to 0. So F naught of X that lives in here goes through F naught, and then goes down into B, which goes down into 0.
Okay.
Or actually, the easier way to do that is just to go this way.
Yep.
but F is an injection. F is an injection. So X equals 0 because the kernel of our modules being trivial is biconditional to the notion of injectivity.
Okay.
So X equals 0 and F naught is injective. So then the kernel of F naught is equal to 0 implies that we are exact at Ker alpha. And so then next we can kind of use the same trick. We can plop something in the kernel of B, and then we can say, all right, well, if we plop something in the kernel of B, then its image in G naught goes to 0 like this, or it goes to 0 like this. And either way, we get exactness.
Mm-hmm.
And so then the sequence is exact at Ker beta. And so then we still need to prove.
That's pretty intuitive once you do the Ker alpha one.
Yeah, like literally it's just the one trick, and then it's like, oh wait, you just like chase diagrams. That's awesome. And then again, since the whole issue here is proving that the differential exists, we don't need to worry about that yet. So we've shown so far that we're exact at Ker alpha and that we're exact at Ker beta. And I think that since we don't have the differential defined yet, we don't need to show exactness here. So 0 into Ker alpha, into Ker beta, into Ker gamma is an exact sequence.
Mm-hmm.
And then I'm going to hazard a guess that we have a similar trick for co-kernel sequence. But let me check. So in the sequence with co-kernels, since the kernel of the map from Coker gamma, okay, yeah, we go backwards. Since the kernel of the map of co-kernel gamma into 0 is 0, no, wait, hold on. The kernel of the map from Coker gamma to 0 is Coker gamma. Yeah, that is true, because it's an abelian category. Right, okay. So the kernel of this map is Coker because everything goes to 0. If we prove that G2 is a surjection, then we'll have shown exactness at Coker gamma. So if we show that this is a surjection, then the image of G2 is hitting everything in Coker gamma, which is the entire kernel of this map. Does that make sense?
Yes. Yeah.
And so then to show that G2 is a surjection, we just want to put something in Coker gamma and show that it traces back eventually to Coker B. And we're given that since the Coker of gamma is really equal to C prime mod the image of gamma, then we have something in the kernel of C that basically gets sent to 0 in here and ends up here.
Mm.
And then I think since we're given that A, B, and C are exact, this little thing ends up back in B, which commutes down to B prime, which commutes down to Coker of B, which ends up in co-kernel of gamma, and of course this thing traces down as well. And so we get a surjection. It is like diagram chasing on a whole nother level here.
Yeah.
Do you want me to walk through why we get that G2 is a surjection?
Yeah, could you?
Yeah, I can do that. So, okay. So basically, gamma gives us that the co-curve of gamma is the image here, C prime, mod, sorry, it's C prime mod the image. So it's everything left over after we get rid of the image here. And so anything that ends up in the coker is implicitly in the kernel of like this inverse mapping.
Right.
Um, and so we get that if it ends up in coker, it must be in the kernel of gamma. But we already have that G naught is exact, right? And so we get something that either pushes down or pulls back into B. And either way, it's going to commute nicely, that we can pull back to something in B.
Oh, okay.
And then once we're in B, it's totally fine because, you know, we can drop something from C into C prime, but we can also drop something from B into B prime into C prime.
Yeah.
Once we get into C prime, then we have exactly shown that we can drop something down into B that drops down, or into, sorry, from B prime into co-curve beta,
Yeah.
and from C prime into co-curve gamma. And once we like drop that down,
Yeah.
then we end up getting the notion of surjectivity that we picked something arbitrary in co-curve gamma, we mapped it back using the properties of co-curve to Kerr gamma, dropped it down into C prime, and then also into beta.
Right.
B prime, co-curve beta.
That makes sense. So like towers of Cartesian diagrams on a whole nother level.
These aren't even Cartesian diagrams, actually.
Oh.
Yeah.
Huh.
Yeah,
Okay.
so if we're a Cartesian diagram, right, what we would have
Yeah.
is that B prime
Mm-hmm.
is the fibered product of the co-curve beta with C prime through co-curve gamma. And so it
Oh,
all of the things that agree through G2 and then this morphism. Um, and I just don't, I mean, it very well could be a Cartesian diagram. It might be. Maybe
okay.
that's an interesting exercise to try after we get off. Um, but then, yeah, basically,
Yeah.
like, yeah, uh, we don't need it to be a Cartesian diagram here.
Okay.
So then, yeah, we've shown now that co-curve gamma is this thing which is exact. Wow, that's a way to say that. And then basically the rest of how this is going to go is instead of like this mapping into zero,
Yeah.
giving us a natural injection. No, not a natural injection. The trick here was that when we mapped this into zero, everything was in the kernel of the co-kernel, or everything was in the kernel of this morphism. But then the kernel of G2 are all of the things that go to zero within co-kernel gamma. But then everything in co-kernel gamma actually goes to zero. And so we get the same kind of like by commutativity. Anything that's in the kernel of G2 is in zero in co-kernel gamma, but that also gets mapped to zero. And
Okay.
so it adds like an arrow like this.
Yeah.
It lets us treat like the kernel of this as an extension of the kernel of Coker.
Okay.
Um, and so then, yeah, basically showing that F2 is a surjection works the exact same way as it did for showing that Coker of gamma had G2 as a surjection.
Mm-hmm.
It's just diagram chasing. And so with that, these two sequences are exact. Now,
Yep.
we still haven't shown that we have this thing. We don't have the differential yet, right? We need to show the differential exists between kernel of gamma and the co-kernel of alpha. And that's actually
Right.
not implicitly obvious because like the way you would want it to work would be like something along the lines of like maybe that.
Yeah.
But I don't, yeah. We basically just want to show that stuff can end up like starting here can end up in here.
Mhm.
But that commutes.
Yeah.
Um and then we need to show that it's a long exact sequence. Okay. So, let me like, is there a way I can just save this? I think, yeah, save. Okay, now this is a sticker.
Yeah.
And so I can just plop it in. Um, oh, that's awkward. My girlfriend loves me. That's a nice thing.
Yeah, that is.
There was like not that many people watching this, surely. Um, if you're watching this, my girlfriend loves me. That's awesome. Um, um, okay, let me try saving this a different way. Um, oh my gosh. So what we're gonna do is we are going to pick something. Um, ooh, my Apple battery is low. We're gonna pick something in Kerr gamma. We're gonna diagram chase down to co-kernel of alpha. Um, and so how do we get that? Um, so if we let C be in capital C, such that it's in the kernel, then we get, okay, let my Apple Pencil charge, and then we can
Yeah.
get into this. I guess it's worth noting that like the kernel of gamma is a defined injection into C
Okay.
because its kernel is trivial.
Right.
Any day now. Um, yeah. Yeah. So I guess I'll talk a little bit now about like while we're waiting to prove the rest of this.
Mhm.
This is giving us like a good understanding of exact sequences, and where that's going to help us is that we're going to be able to do the rest of these exercises in Vakil
Yeah.
about homological algebra, and then it's going to kind of tie together. And he uses almost the same approach to homology, cohomology that I used in my paper because I wrote it based off of mostly his book, except for I also referenced a few papers from U Chicago's REU that did a really great job. Um, but yeah, we're gonna spend like a long time going through this section. For
Okay.
context, we've made it through like a page and a half today. Because he defines like the homology groups,
Yeah.
and then he talks about complexes, and he says, "Hey, you should do the snake lemma if you feel so inclined." Um, and I think it's an important thing that everybody should see once, and so we did that. Um, And then he says we can factor any complex into short exact sequences.
Yeah.
And then we can define the dimension of a homology group. And that is a really good exercise. Wow, I did not realize how good that was when I first did that. And then we'll define a category of complexes, and we're going to show that that's an abelian category. And then, yeah. Then we'll talk about like homotopic maps on chain complexes. Um, and then we'll talk about right exactness, left exactness, derived functors. And then yeah. And then it goes through some other stuff about like adjoints commuting with limits. Um, okay, so we're Apple pencils up. We're chilling.
Yeah.
Okay, so let so proof of snake lemma. We're now ready for it. So let C in C with gamma of C equals 0. Then C is also in the kernel of gamma, basically by construction. And then since G is surjective, right? So let me go ahead and mark. So I think I've provided this notation before, but basically a hooked arrow like this means injection, and then an arrow like this means surjection.
Okay.
So it's just an easier way for us to keep track of everything. So we have C in the kernel of gamma, and then G is a surjection. Since G is surjective, there exists B and B with G of B is equal to C. This B is not unique, right? It's only a surjection, so we don't have an injection. Otherwise, B and C would be bijective objects. And since I guess we're working in the category of modules, it would be an isomorphism. So that's like not something we want to endow this with.
Yeah.
But basically, um, so 0 is equal to gamma of C is equal to gamma of G of B. But then this is equal to G prime of beta of B by commutativity, right? So we have, what's a color? Okay, here. So we have C here. C gamma of C is equal to 0. We have C here. We have G of C. And then we have beta of G of C is equal to and then this is equal to G prime of beta of G of C. So does that make sense what we've set up so far?
G of B or G of C for the G prime of beta?
G of C. G of C.
Okay.
Right, so it looks like I guess maybe arrows are not what I want to use here, but whatever.
Okay.
Yeah, so that's kind of like the order that we're going in. And so basically, therefore, beta of B is in the kernel of G prime, right? Because this equals 0.
Yep.
So this is in the kernel of G prime. Um, and so now we have kernel of G prime out there. Oh, but then this is the image of F prime because this is an exact sequence, right? So this is an exact sequence. So the kernel of G prime is equal to the image of F prime.
Yep.
Image of F prime, because we proved in this lemma that these were exact sequences.
Yep.
And so then there exists an A prime in A prime such that F prime of A prime is equal to beta of B. So F prime of A prime. So A prime of A prime is equal to beta of B.
Mm-hmm.
And then we know that this factors to 0. And this choice of A prime is uniquely determined
Okay.
by of. So I'm going to say there exists unique A prime. And then this goes into Cooker. And so now we have chased C all the way down into Cooker of alpha.
Mm-hmm.
And so the way that we do this is we say, so delta, not delta, the differential of C is equal to A prime. Mod the image of alpha in Cooker of alpha. Right? And so that is equivalent to commuting everything that we've done here.
Yeah.
And so there kind of comes this question of, all right, we've set up this differential thing where the differential is from the kernel of gamma to the co-kernel of alpha. But basically, all this hinges on potentially the choice of B in this surjection that goes to C. And so we need to do two things. Basically, that delta is actually, or I keep saying delta, that the differential is well defined. Right, this map from the kernel of gamma to the co-kernel of alpha is well defined. That like everything in kernel of gamma gets sent to something in co-kernel of alpha.
Mm-hmm.
But then we also need to basically say, all right, our choice of B doesn't matter, right? We can pick anything in the pre-image of C
Yeah.
Again, noting this surjectivity here being the big thing that like screws things up potentially, right? And I'll even add this in. Does B matter? It isn't unique, right? And so basically what we'll show is that the differential is well determined, and then B doesn't matter. And so I'm gonna hand wave at this part because there's other stuff that I want to get to today. But if you want, I can maybe write it out for you some other time.
Okay.
So since we chose C arbitrarily, and we chose an arbitrary B that just equaled C, if we pick a different element like B prime, then we eventually get that A prime is congruent to a other thing, right?
Mhm.
Like if we pick what's a color I haven't used yet? Hold on. I don't really like this color, so I'm gonna pick something new. Let's do like an orange. That works. So let B prime not be B. Then we get beta of B prime is equal to beta of B, I think. Um, just by transitivity of F prime of A prime, right? No, no, not that. Definitely not that. Sorry. Um, but basically, these things both have the same preimage here, right? So we get like an A star that goes to B beta. And the thing is they might not be the same in the category of sets. Like if we take a forgetful functor from A prime to the category of sets, A star and A prime might not be the same thing. But because we're doing this whole business of mod the image of alpha, they are congruent, and that's how they end up in the same image. Does that make sense?
Yes, it does.
Yeah. And so then, yeah. To show that it's well defined, it pretty much just kind of falls out of the fact that we can diagram chase successfully. Um, right, we picked an arbitrary C, and we followed it through into Coker of alpha, and basically we showed that like as long as these things exist, if these sequences are actually exact, then we have the things that we need to chase diagrams successfully. Okay. So showing that this is a long exact sequence. So now show that um, that this whole thing is long exact. Um, and I want to make sure, let me see how she defines long exactness. I want to make sure that that lines up with what we're using as our functioning definition. Um, so, um, Yeah. Yeah. No, it's not there. Where would that be? Maybe under modules. No. Okay, well then I'm just going to use Vakil's definition of a long exact sequence. So a long exact sequence is a sequence of short exact sequences that happens to also be exact. Wow. Where the heck? That's a little annoying. I can't find his definition of long exact sequences. So a long exact sequence is basically something that is an exact sequence. And it is technically an infinite chain of morphisms, but like it can stabilize. So like basically like here it goes off to 0, but what it really does is it goes off to 0, which goes off to 0, which goes off to 0, which goes off to 0. Does that make sense?
Yes. Yeah.
So that is a long exact sequence. And so really the only thing that we need to show now is that the differential is induces exactness at gamma and then exactness at alpha. So yeah, we need to show exactness here, and we need to show exactness here. And so we can do this by set containment, really? Oh my god. I don't want to do a set containment proof. Okay, so we want to say that Kerr gamma to Coker alpha. We want to say that nope. Starting with exactness of Kerr gamma. We want to show that the kernel of the differential is contained in the kernel, or is contained in the image of G naught, and vice versa. That the image of G naught is contained in the kernel of the differential. And so the way that we're going to do this is we're going to do some more diagram chasing. So So let y be in, I think we're going to start with the second direction. Let y be in the image of G naught. Which is that contained in the kernel of gamma? I don't think we're given that. I think that's an error. Okay.
Wait, how can one be contained inside the other? Like, how can they both be contained inside the other?
Because that's what we're trying to show. So the definition of an exact sequence,
Yeah.
I don't actually know if I wrote it down here, but the definition of an exact sequence is that the kernel of this thing is equal to the image of this thing.
Oh, okay.
Right. Or like alternatively that the homology group, which is the kernel of this thing, mod the image of this thing, is zero at this object.
Okay.
Right. So like, yeah. What we want to set up here is that the homology group at every single object is zero. And that's just it's an example of homology.
Oh, okay.
Yeah, in like an algebraic sense.
Yeah.
So let y be in the image of G naught. We want to show that the differential of y is equal to zero. Right? Is that what we want to show? We're putting y in the image of G naught, which lives in this sounds like we're proving that the co-kernel of alpha, hold on. Okay, I'm just gonna abandon the notes here and prove this the way that I think it makes sense to prove it. And then I'm going to go back and convince them because I think if I remember this lecture correctly, I think this is where she had to switch to the board. But I could be wrong. Okay, so we want to show that the differential of y is zero, meaning that if we have something in the image of G naught, that it's in the kernel of G naught. Or sorry, that it's in the kernel of the differential. And this will show this direction. So we know some facts about y. So we know that the delta of y is equal to some a prime mod the image of alpha. And then from our diagram chasing, we know that we get this by basically we have some g of b that's y. So g of b is equal to y. And then with a little bit more diagram chasing, beta of b is equal to f prime of a prime. And then since y is in the image of G naught, there exists x in the kernel of beta such that G naught of x, so again, G naught of x is up here. And we're moving like from back here to Kerr gamma. Such that G naught of x is equal to y. So G of x is equal to y. And then diagram chasing some more. G prime of beta of x is equal to gamma of g of x is equal to gamma of y is equal to 0. Since y is in the kernel of gamma. And then since x is in the kernel of beta, beta of x is 0. And then we get delta of y comes from a prime in a prime with f prime of a prime is equal to beta of x is equal to 0. And then since f prime is an injection, we know that a prime is equal to 0. So again, kind of going up here, our kernel is trivial. This thing lives in the kernel. It must be 0.
Mhm.
So this means that the differential of y is equal to 0, and y is in the kernel of the differential. And so our first containment is proved. It works pretty similarly going the other way. I'm just going to bump that to an exercise because we're running out of time.
Okay.
It also works like you do the same type of containment proof where you do diagram chasing from co-cur, except you have to show it with F2 and the differential.
Okay.
So it's just painful. Like I can maybe type up the proof, but it just kind of sucks. It's a lot of diagram chasing. I don't really want to do that right now. But yeah, I'll send you something so that you can like work through it more if you want to.
Okay.
So yeah, wrapping up a little bit here. So okay, let me introduce Vakil's notation about homology and cohomology. So dot box towards the homology. So if we usually write homology as like AI plus 1 into AI into AI minus 1 by f of I plus 1 and then fi, right? Then the homology group at AI is the kernel of fi mod the image of fi plus 1. And then we'll induce the cohomology as like this thing called a cochain. So if this is a chain, right, like this whole thing is a chain, then the cochain is sort of like the arrow reversing, but it's because we apply like a contravariant functor, right? And this is where we got the idea of cohomology and right-derived functors was like cohomology stems from the idea of we want to switch all the arrows and we want to do it in a way that like changes the structure or keeps the structure the same. But either way, we want it to be intentional. So like usually what you do to derive cohomology is you say, okay, well, we have our topological space and we have like, the chain that we want to reverse things on. We really want to do this by making it contravariant, right? And so we take a contravariant functor, we put in, our sequence like this, where
Yeah.
A dot is all of this, right? So the entire sequence is
Mhm.
A dot. Induces a cochain complex. Wow, that did not spell. Um, and that cochain complex usually looks like AI plus 1, AI, AI minus 1. And then how I guess well, okay, hold on. I get this would be HI of A dot. There we go. And then the cohomology group. So this is homology. Then the cohomology group is denoted H superscript I. And it's kind of just implicit, for the most part, that the functor that we use leaves everything the same but just dualizes the arrows. You can definitely like use some weird functors, but you don't need to. And so we're not going to deal with that until we need to deal with that. And so, yeah, basically, as a theorem, an exact sequence that looks like A dot defined by A to the I minus 1 into AI into A to the I plus 1 by F to the I minus 1, F to the I, F to the I plus 1 can be factored into short exact sequences at each I. And what that looks like is 0 into the kernel of Fi into, hold on, that did not get on the right spot, there we go. Kernel of Fi into AI into the kernel of Fi plus 1 into 0. And so then what this looks like, and the induced morphisms, I'm pretty sure, hold on, I think it is Fi here. No, it's going to be its own thing. But basically, like, you can think of this as inducing, like, something that looks like this, I minus 1. And then this would be I minus 2. Right. No, I minus 1. And then this would just be Fi. And then this would be plus 1. And then everything would scoot over some. This would be plus 2. And then the chain complex would look like this. And so this is our notion of factoring things into long exact sequences. And it's worth noting, like, these arrows also exist by commutivity.
Yeah.
Right. And this is where like the snake lemma becomes useful. But like only so useful. And so yeah, it can always be factored like so. We can also obtain another factoring. So you can also factor into 0 to the image of fi minus 1 into the kernel of fi into the cohomology group of the cochain complex into 0 as a short exact sequence. Is short exact. And this is literally by construction because the cohomology at AI is quite literally like if, let's use some highlighting here. So if this is the kernel of Fi, then this is the image of Fi minus 1 overlaps here as the cohomology group. Right. And then similarly, and I'm pretty sure on this ends up being the homology group. So and then that would just be moving everything around a little bit. So it would be the kernel of Fi and Fi minus 1, but it would be dualized and it would look like 0 goes into the homology group, which has the kernel of Fi, which has the image of Fi minus 1, which has 0. And that would be the homology group.
Okay.
So we've made it like as far as I think I want to make it today. We did a bunch of really important stuff. We introduced kind of like the intuition of cohomology for sheaves, and like how we measure things with like failure of exactness. We talked about the snake lemma and improved most of it as like a way of getting used to chain complexes. And then now we've proved some things about like homology and cohomology groups in long exact sequences and like factorization of long exact sequences into short exact sequences. And so what we'll pick up with next time is describing certain types of exact sequences, and then showing some things about dimensions of homology groups. And so that'll tell us some interesting data. After that, we'll do some more theorems about like basically cohomology inducing like a long exact sequence of short exact complexes.
Yeah.
And then I think next time the big thing that I want to end up proving is that this thing called the FHHF theorem.
Okay.
Yeah. And that's where I think we'll leave off next time. And then at that point, we get into like kernels, limits, co-limits, and adjoints communing with each other in long exact sequences induced by homology. So I think we have at least 2 or 3 lectures, so 2 or 3 days for us just on this material.
Okay.
And then we get to move on to to sheaves, and that'll likely be a lot easier.
Perfect.
Yeah, so we'll talk about like some examples of sheaves beyond like what I said today, and then we'll probably just follow like whatever Vakil has. So yeah. All right. Well,
All right.
thank you so much. I'll go ahead, stop
Yeah.
the recording, and yeah. Cool.